Flight, the dream that has fascinated people throughout time. From early attempts at self-power to rocket power, the means of generating propulsion has gone through many metamorphoses in our quest for faster, simpler, and more efficient engines. It's very clear that aside from the unquestioned need for safety, an efficient engine is the basis for secure, enjoyable, exhilarating flight. To that end, Phil Hoponick and Todd Johnson have run workshops nationwide on caring for and rebuilding the engines in personal aircraft. In response to feedback from aviators, owners, and home builders who have attended these workshops, we've asked Phil and Todd to show us the guidelines for rebuilding some of the more popular engines in use today. While some of you will be part of that growing group of home builders building your own craft, others of you will be like many of the folks Phil and Todd meet around the country, those who want to know when an overhaul is called for and what is involved. Like car owners, some people take special care of their machines, while others wait for a problem. With an airplane, maintenance means safety and peace of mind. An overhaul is recommended when your engine is leaking oil, your engine is using oil, your engine fails a differential compression test, you've reached your TBO, time between overhauls, recommendation. You've reached the manufacturer's time limit on an overhaul schedule. There are 2,000 hours on your engine. Additionally, preventative maintenance can be done to the manufacturer's specifications. This tape deals with the Lycoming 0320 engine. While descriptions here are thorough, you'll note that we continually remind you to consult the manufacturer's manuals for tolerances, torques, and other specifications. Different model years, model alterations, and design tweaking won't change the basics of the overhaul, but they will require you to maintain diligence in attending to the details. So, enjoy the tape, whether you use it to rebuild an engine or just to become more familiar with your engine's internal workings. It's great for honing your skills or just making you a more knowledgeable aviator. Our demonstration begins at Mattituck Aviation, the world's largest engine rebuilders. Located on Long Island, Mattituck Aviation very generously allowed us the use of their facilities to perform our rebuilding. While we're beginning with the reassembly, you have to have completed certain tasks not covered here to reach this point. At this facility, engines are shipped in or actually flown in. The engines are removed, disassembled, and everything is cleaned by water, chemical, brush, or machine. All tolerances are checked, and parts are either brought up to specifications, or if that isn't possible, they're discarded and replaced. The reassembly centers around the crankshaft, which we've mounted vertically on a fixed column. A pan collar at the bottom is a convenience. It helps with holding parts and tools. The advantage of this mounting becomes apparent when we need to rotate the engine by hand to position the pistons and perform other timing operations. We also mount the crankshaft vertically so we can visualize the placement of the engine's parts. We understand that this is where the number 1 cylinder will be, the number 2 cylinder, and so forth. This allows us to further visualize the relationship between parts such as the sump, the camshaft, etc. The first step takes place as a subassembly. The left half of the crankcase is painted with an adhesive. The adhesive is used to hold a 100% silk thread that actually works as a gasket. This thread is routed to the inside of any bolt holes so that no oil can escape through the bolt holes or the parting surfaces. The silk thread is left long so that it will meet and be a continuation of the nose seal that will be used at the crankshaft opening. Next, we put in the bearing inserts. There have been updates in a few different styles of this part, so refer to your parts manual for specific parts numbers. Now, we put in the tappets, which actually give movement to the valve train. As with most assembly steps, everything is lubricated. The camshaft is now fit into the crankcase. O-rings are fit into the bolt depressions so that the crankcase halves seal when brought together. The front main bearing can be 4-piece or 2-piece. If your engine uses a 4-piece main bearing, it is placed in the same manner as the center and rear main bearings. Our engine uses a 2-piece front main bearing, which is put in differently. It must line up with the dowel posts in the crankcase. Position it while the case is open and, with a pencil, mark the spots on the bearing where it must meet the dowels. This will allow you to more easily position it later. The crankshaft seal is now placed around the crankshaft and will be coated with adhesive when the crankcase halves are brought around it. The crank gear is now positioned on the top of the crankshaft. There's an AD, airworthiness directive, out on this part, so this plus the manufacturer's service bulletin must be strictly adhered to. The process includes tapping down and placing of the bolt with a lock tab. This is then torqued, again paying careful attention to the manufacturer's bulletins. There's an inspection in this area with a feeler gauge. Any part of the gauge which goes under at these points would warrant taking it off and an inspection being done. The objective here is to get the gear down in the counterbore and square with it. If it's not flush and flat, you could have a lot of trouble down the line and in the air. We now assemble the connecting rods with the correct bearings, the size needed for the crankshaft. A crankshaft can be reground to minus tolerances rather than being replaced. This must then be accommodated by correctly matching the bearings. The connecting rods and crankcase are numbered, and you always keep the corresponding numbers together, 1 to 1, 2 to 2, etc. We now see why we originally spoke of mounting the crankshaft vertically for purposes of visualizing the final assembly. The vertical mounting and raised numbers are both aids in this visualization process. The connecting rods are assembled on the crankshaft with the numbers away from where the camshaft will be and toward the sump side. We now lubricate the bearing areas, the thrust surfaces, and the threads. We now face the crankshaft and orient it so the lower, or number 1 piston, is extended to what would be called top dead center, or full firing position. By being in this position, the rest of the engine will sequence easily as we proceed. We now assemble. Refer to your table of limits for the correct torque on these nuts. These are one-use only nuts and bolts. This means that if you need to back off or if they bind, you should just throw them out and use new ones. Tolerances are very crucial here, and the material stretch and change caused by the tightening process can cause a second attempt to be less than accurate. The best method to torque correctly would be to torque to half level, check that all parts moved correctly and easily, and then retorque to the next level until you reach the correct point. We now have reached a point where we have two sub-assemblies which are about to be joined. After joining them, we're not going to be able to go back and separate our work. So here, we suggest having a knowledgeable friend inspect your work so far, or walk away for half an hour or so and come back with a fresh perspective and review what you've done. This is a technique we'll be suggesting at several points during this rebuilding process. Now, being satisfied that all is correct to this point, we're ready to join the sub-assemblies. This means lubricating all the bearing points and thrust surfaces. The front main bearing is lubricated and placed at the front main crankshaft journal. Again, we can visualize knowing that the crankcase will go on here, the bearing will go here. Since this is a two-piece front main bearing and thus we marked it with a pencil, we can line up the dowel holes correctly. We'll place adhesive on this nose seal and on the receiving part of the crankcase. This is a contact cement recommended by the manufacturer, and it will adhere when the halves are brought together. And since it's a wearing part, it gets lubricated. This is done because the crankshaft can grab the seal and spin it, causing crankcase damage. We now position the crankcase half over the extended number 2 cylinder. The bearing is adjusted to fit correctly over the dowel markings. This means positioning rotationally and vertically. An extra set of hands will be necessary in leveraging the crankcase. If the dowel holes did not align, when you tighten the crankcase, the result would be a pinched bearing that would not allow the engine to rotate. The seal is now raised into position, keeping in mind to rotate the split so that it does not align with the crankcase parting seams. A 10 o'clock or 2 o'clock position when viewed from the top. This way, the seam will not be aligned with the crankcase halves. With no contiguous seams, there are less easy paths for potential oil seepage to follow. As a rule, we will always avoid allowing seams to line up. You can see a machined groove in the crankcase into which the seal can set. There are several styles of seal. If this doesn't describe yours, refer back to your manufacturer's manual for installation instructions. A gauge must now be taken to make certain that there is clearance between the crankcase and the part of the crankshaft called the oil slinger. The oil slinger is merely a saucer edge near the other side of the thrust face that by centrifugal force induces oil to go out and back into the crankcase. This saves the seal from being excessively oiled and prone to seepage and leaks. The crankcase is levered to accommodate the manufacturer's recommended feeler gauge clearance. Without this clearance, this is another spot that would be subject to immediate wear. If all steps so far are correct, you'll notice that there is sufficient crankcase end play. The left half of the crankcase is now fitted. This also requires a second set of hands. Bolts are put in left to right as per the manufacturer's recommendation, with a washer on both the nut and bolt head sides. An internal lock washer safeties that nut in place. As you continue around the crankcase, your assistant should lightly hold the halves in place. The crankcase at this point should be viewed as a whole machined part, and the tolerances established must be scrupulously maintained. The bolts are lightly tightened so that the crankcase may be aligned by the through bolts. We check that there's no binding, that the crankcase end plate still exists, and that the camshaft turns. We can now put in the engine through bolts. These bolts seal, align, and hold the halves together and hold the cylinders. They must be hammered into position. They are neck down in the middle so that while the ends are sealed, the middle can still expand and contract with the heat of the engine and still be a holding force. A screw-on cap allows the bolt to be struck with a hammer, but care should still be exercised, since excessive force can still cause thread damage inside the protective cap. There are 8 bolt positions. The lower bolts do not have a cylinder on each side, so a spacer takes up the length. The top 2 bolts are actually studs built into the crankcase right half, and the left side fits onto them. These bolts therefore need no spacers on the built-in side. The 4 center bolts are hammered in as described. You can visually gauge the correct placement, and later, nuts on either end can pull the bolt through or back to whatever position is desired. The remaining crankcase nose bolts go through the O-rings that we have glued into the recesses provided for them. Use a light grease to carefully screw these bolts through. The O-rings are good seals, but they are silicone O-rings and will tear to bits if you try to screw a dry bolt through them. The light oil prevents this. If you see any O-ring material at the exit end, stop and go back and replace the O-rings. Any O-ring damage all but guarantees an oil leak. By the way, any disassembly at this point requires a replacement of any sealing part, such as the silk thread. Nut and torque the bolts as per the manufacturer's recommendation. We will now bolt and torque the through bolts to the specifications in the manufacturer's manual. This uniform crush on the case seats all the bearings and rounds up everything. We now check for movement, making sure there's no binding. Since the case is now as tight as it's going to get, we can now put in the remaining smaller bolts, torquing them. 3 bolts go in the sump side, and they are safety wired. All internal parts have some type of locking device to prevent vibration or wear from unseating them and thus causing unseen internal damage. Of course, these bolts are tightened to the recommended torque. The 3/8 stud that holds the crankcase together at the gear end of the camshaft has to be torqued and wired. Earlier models may have a complete through bolt. We now address the gear section. Gear idler shafts are positioned and locked plates are put on for safety. They're torqued, and then, to prevent bolts from loosening and possibly slipping into the engine, the ends are bent up. Galley plugs are now installed. We now position the gears. We must reference back to the number 1 cylinder, which we want extended to top dead center. This is because we want the crankshaft to be timed to the camshaft. This allows the valves to operate properly depending on where the piston is in the cylinder. We extend the number 1 cylinder, we locate the timing marks on the camshaft, those 2 dots there, and we locate the timing marks on the crankshaft gear. The timing gear drives the camshaft, drives the magneto, and has an eccentric, a cam, which drives the fuel pump. The timing gear has marks which we match to the camshaft and crankshaft timing marks. We match everything, and the timing gear falls into place. The next gear turns the magneto, and while it is similar to the preceding timing gear in that it has timing marks, it's not timed to anything else, so the marks are of no consequence. This is the tachometer drive shaft. It's attached to the camshaft. A tachometer cable will be attached to connect it to the instrument panel, where it will tell you the engine's RPMs, revolutions per minute. It's held in by a snap ring. Be sure to rotate the snap ring opening 90 degrees to the tack pin opening. Again, we never allow openings to line up. This is your oil pump. It consists of the housing and two impellers with a drive shaft. These are assembled. Use of a heavy lubricant is important here for the initial priming of the system. This oil pump assembly is attached to the internal side of the accessory housing by means of 3 castle nuts and 3 plain washers which are torqued to the manufacturer's specifications and safety wired. When joined, the protruding shaft engages the crank gear. A seal is applied to the tachometer drive shaft housing. Next, we install the fuel pump push rod, which is needed to drive the fuel pump lever. We've now reached one of those points where we're about to close something up, and so we should have our knowledgeable friend check our work while we step back or step away for a break. Refreshed, we can review what we've done with clearer eyes and move on. We now come to the accessory housing. Blue silicone will be used at several important junctures. One is here where the silk thread comes out of the crankcase. No matter how well milled the halves are, a slight valley could form where the halves butt, so a drop of sealant is placed and the thread is bent over. The accessory housing now gets an accessory housing gasket. Use a sealant recommended by the manufacturer. Now all the gears and shafts are lubricated. Now, as you're ready to position the accessory housing, you want to be sure that the drive shaft is aligned with the crankshaft gear that will be driving it. By holding the shaft in position with your hand under, guide the housing on, and with this for basic alignment, shift it slightly until the whole unit seats itself, sort of snapping into place. Never seat this by screwing down the bolts. Anything more than light tapping would suggest something's out of line or incorrect. Don't force anything. At this point, put the housing bolts in and torque them to the manufacturer's settings, and do it in the correct sequence. We're now ready to attach the oil sump. The oil sump is a large unitized piece that has air manifold tubes that allow air induction and lead to where the carburetor will be. The body will contain the engine oil. When the sump is fitted to the crankcase, you can see that splash oil will flow over the gears we've lubricated, providing for their ongoing lubrication. A small hole in the sump allows for placement of a pre-pump oil screen tube. This is a filter which precedes the oil pump, which in turn is followed by the oil filter. It screens out large particles which could clog the oil pump or filter and hinder oil flow. During an oil change, the screen is cleaned and the oil filter is cut open. The type and size of material found can give accurate clues as to what is going on in the engine. The pre-pump screen is fitted with a pressure gasket and is turned the correct number of degrees. It's then safety wired when mounted. In joining the sump to the crankcase, we now see that the accessory housing gasket was left long on the crankcase. This is done to accommodate any variation and allow for cutting to correct size. If everything's okay, these can now be trimmed off and dots of blue silicone applied to the 3 spots where joints occur on the face of the joining surfaces. Adhesive is applied, the gasket is positioned, and the sump is placed. Bolts are torqued to specifications and in the recommended order. This engine can take an oil screen or an oil filter. The oil filter spin-on adapter is easily attached. It gets a gasket, is adjusted to position, bolted, and torqued to specifications. The adapter has 2 inputs. One is for a temperature probe which operates the oil temperature gauge on the instrument panel. The other opening houses a vernotherm bypass valve. This thermostatically self-operated valve exposes a hole to the oil cooling system. When the vernotherm heats up, it expands and covers the hole, allowing oil to flow through the oil cooling system. This is a simple mechanical system which cannot be worked on or adjusted. When it no longer works, it's thrown out and replaced. The vernotherm is simply screwed in and safety wired. We've now come to the vacuum pump drive adapter housing. The vacuum pump, which is outside the scope of this tape, is driven by this drive and creates vacuum necessary for the operation of some of the gauges on the instrument panel. The housing gets an oil seal, a thrust washer, which prevents it from eating itself, and the drive gear. They fit to each other and are then positioned through the gear housing to be driven by the rotation of the camshaft. The unit will seat itself and can only go in one way. A small internal oil passage allows oil to lubricate the shaft while it's in operation. There is also a small protruding pin which guides correct positioning. Don't force anything. The oil pressure relief valve is now screwed into position. This valve is a spring-loaded ball. The spring holds the ball against the chamfered relief hole. Excess pressure pushes the ball off the opening and allows the pressure to be relieved. You can create any pressure relief level you want by using various combinations of washers and springs. Your manufacturer's guide will tell you how to do this. The valve is screwed in with a crush washer and safety wired. The oil pressure fitting is now installed. The dipstick housing is now screwed into the crankcase. It's fitted with a gasket and safety wired. An O-ring seals the upper stick end of the housing, which is applied when the engine is installed. This is the stage at which we generally paint the engine. Over time, we've developed high-tech methods of protecting the internal engine from splattered paint. Be creative. You'll find the means to block all the engine openings. We've now reached the point of installing the cylinders. Reconditioning cylinders is specialty work requiring special skills and equipment. We don't cover that here. When the engine was dismantled, the cylinders were refurbished. The guides, seats, and valves have been replaced and clearances reset to the manufacturer's specifications and tolerances. They also have been repainted. You can now check the cylinders. Check piston skirt size to the barrel clearance. Cylinders and pistons are separate pieces and both come in oversizes. We remove the ring and insert it into the cylinder to make sure that the ring gap, where the ring ends butt, is to the manufacturer's tolerance. The rings are then replaced correctly with the numbers up. We're now ready to assemble. An O-ring sits at the base of the cylinder as an oil seal. The piston is symmetrical and can go in rotationally up or down. We've numbered each piston so that with any engine work, the same piston will go back into the same cylinder in the same position, anticipating avoiding any individual cylinder characteristics or quirks causing changes during wear. We now put in a full floating wrist pin, which is held in or centered by wrist pin plugs. These plugs may protrude at times and touch the cylinder walls, but not to the detriment of the engine. The cylinders are now ready to be positioned. Care is taken to rotate the ring brake gaps approximately 1/3 of a turn off of each other. This, again, is just an added precaution to eliminate a direct path of escape for exhaust gas from the cylinder. A ring compressor compresses the rings to allow them to slide easily into position. The cylinder is now positioned, bolted, and torqued, as always to manufacturer's specifications. We now begin the installation of the valve train. These hydraulic units are all the same, but they're milled units. They come apart for cleaning, but if anything happens to either piece, throw them out. Don't try and match them with other mates or you'll have a rough-running engine. The unit is not full of oil now to allow for what we call a dry tappet, which allows the internal spring to work correctly. Oil would create a false resistance and give a false indication of the dry tappet clearance. The unit sits in the tappet we installed with smooth hole in, spring out. A lifter cup is now installed, which is nothing but an adapter going from a flat surface for the spring end to a concave surface to meet the pushrod. All were lubricated before installing. To install pushrod tubes, place pushrod seals for the crankcase end. The other end of the pushrod tube has an O-ring seal for the cylinder. They get kind of pushed on. The tubes are held in place at the cylinder head by spring retainers on the studs, some of which may require washers. A lock tab goes around the spring, gets a cap nut, and is torqued. Part is then bent up. The exhaust valves have rotor caps placed on them, which allows the valve to continue to rotate while it's in operation. Some engines have these rotor caps on the intake valves also. We're now going to put in the push rods and check the clearance between the rocker arms and valves, the dry tappet clearance. All these components are pre-oiled. The rocker arms are cast the same but milled differently. Some have small holes. The rods are pressurized by the oil system. The rockers with the holes go to the exhaust side. The exhaust valves work under great heat and stress, so these small holes spray oil, lubricating the exhaust valve. The oil pressure in the intake arm ends at the rocker. Without the heat and explosions of the exhaust side, its oil cooling needs are not the same. This oil dribbles down to the bushing and is gravity fed back to the system. We now rotate the engine to bring the cylinder to the top dead center firing position so we can insert the rocker pin. The rocker pin has a couple of Teflon buttons on the end so it doesn't wear against the rocker cover. The dry tappet clearance is now checked with a go, no-go gauge to meet the manufacturer's specifications. Go, no-go means that the minimum side, go, should fit, and the maximum side, no-go, should not fit. Any misfits in the clearances are adjusted by changing the actual rod. The manufacturer makes rods of 4 lengths, and a go, no-go means you change rods to get the correct fit. The rocker covers can now be put on, consisting of simply a gasket and rocker cover screws. We now look at the carburetor side. The air-fuel mixture is coming from this side, so the manifold ports have to be connected. The connecting elbows have a tie collar. The gasket gets coated and the collar is screwed down. Be careful to set the flange collar and gasket correctly, or there'll be a gap allowing an intake leak. When correctly positioned, the elbow will set deeply in the collar. When viewed from the rear, the centering is more apparent. The sump manifold end is connected with a conventional flexible sleeve and 2 worm clamps. The sleeve fits over the manifold stem and the elbow, with one clamp securing the sleeve at the manifold and the other securing the sleeve to the elbow connector. Drainback tubes are now fitted. These tubes are shaped very specifically to the course they must follow, so they're hard to mix up. Each has a rubber connector and a couple of clamps. Each slides over a fitting in the crankcase and is clamped. Each is self-sealing at the cylinder side and is sealed with a B-nut. Oil that settles in the cylinders simply drains back to the sump area through these tubes. The fuel pump is installed, sealed, torqued, and safetied to the accessory housing. The drive is turned by the eccentric that we noted on the timing gear. The only trick here is to be sure the eccentric push rod is at the shortest part of its stroke, so that the matching piece on the fuel pump will allow for easier installation. There's a potential for them to align to the side where they would not operate properly. We now want to rotate the engine to get piston number 1 in full firing position. Placing your fingers over the spark plug holes simulates compression. As you turn the engine, you can hear the compression come up. When we've ascertained this spot, we now place the starter gear support in the dowel holes at the base of the crankshaft. Each engine has a plate on it which indicates the firing point and firing sequence. This engine says 25. This means that the spark should occur 25 degrees prior to the piston being fully extended. This spark is timed to 2 magnetos, one left and one right. Both are the same except for one thing. Since most engines begin firing with the left side, the left magneto has a spring-like collar called an impulse coupling that retards the first sparks. When an engine is first started, it must build to its rotational speed. The normal firing is timed for an engine that has reached normal speed. These first, retarded sparks will fire to more accurately match the initial rotational speed. Flyweights pull in the impulse coupling, which allows the engine to go right back to 25 degrees before top dead center, where it normally runs. In positioning the magnetos, a spacer fits on the opening of the left magneto to take up the space created by the impulse coupling hanging down. The right magneto, not having this piece, does not require a spacer. In placing the magnetos, we must line up the sparks for the number 1 cylinder. Each magneto has an L and an R. This asks for the direction in which the magneto will rotate and fire. This is a left rotating magneto, so we place a thin pin in the L-hole side and slowly rotate the magneto until the pin drops further, indicating it's locked into the correct number 1 cylinder position. Slight turning indicates it's in position by a slight wobble, but don't turn too hard or bring excess pressure to bear here, since the pin might bend and can cause expensive problems inside the magneto that you can't see or won't learn about until it's too late. A coated gasket and the magnetos are placed. The magneto can go in any manner that allows the gears to mesh, but consideration for any possible interfacing with the engine mounts may make you want to rotate it to a more convenient position. The other magneto is also left rotating, so its pin is placed in the same manner. A gasket is again coated and the magneto placed and the pins removed. We're pretty on target as far as timing is concerned, that the number 1 piston is at top stroke and the magnetos will fire correctly. But it's now time to fine-tune. The magneto clamps are put on finger tight for fine-tuning and will be tightened later. We want the points to be just opening because that's when they release their energy to the cylinder. A magneto synchronizer is attached to the magnetos and the pins are removed. The lights on the gauge will go on when the points on each magneto open. We want to be sure that both occur at the same time. This means both lights must light at the same time. The leads from the synchronizer go where the leads from the cockpit will be. We turn the engine to 25 degrees before top dead center to see how close the lights are to going on together. You're allowed a certain tolerance as per the manufacturer. We can hear each one click in on the synchronizer, and they're almost exactly together, which is fine. Adjustments, if they're necessary, are made by rotating a magneto forward or back to more accurately match the 2 sparks to accepted tolerances. Now, you can torque the magneto clamps and adjust the engine for synchronization. The ignition harness is generally attached at the aircraft, since ignition wires are often snaked through the airframe and therefore left in position. If the cap is removed, or when rejoining them at the frame, be careful to match all the numbers, left side to left side, cylinder 1 to cylinder 1, and so forth. Spark plugs are lubricated on the threads and torqued in place as per the manufacturer's specifications. The starter is simply attached and bolted down. And if your engine has an oil filter instead of an oil screen, the oil filter is screwed on, torqued, and safety wired. One last thing, some engines have engine primer leads to several cylinders. The ports to attach these leads have Allen plugs in them. If your aircraft has primers, when you reinstall your engine, this is where they go. This is where the carburetor goes. This is the point where you'll reinstall your engine. A facility such as the one that we're using has the advantage of a test site, so we can easily make any adjustments before reinstalling. All tests being done, we're ready to fly. And that's what it's all about, the thrill and joy of aviation, soaring above the earth, secure in the knowledge that we've made the effort to make our time in the air safe and trouble-free. Our skills as pilots allowed to shine because our engine is dependable.